Hello everyone and welcome to another Big Data London webinar. Today we're looking at real-time analytics and their impact on business operations. So I'm Andy Steed, Content Director of Big Data London, and I'm joined today by Richard Henderson of TigerGraph. Hi Richard.
Hi.
Hi, welcome back in fact, isn't it? It's your second one. These sessions are designed to be interactive, so please do ask any questions to Richard using the questions function at the bottom of the screen, and I'll endeavour to ask as many as I possibly can. At the end of the session, we'll have some time for Q&A. Quick note of housekeeping, if you lose the stream at any point, you shouldn't, but if you do, just hit refresh in the browser and you should just jump straight back in. However, without further ado, I'd like to throw it over to our featured presenter today. So over to you, Richard.
That's great. Thank you, Andy. So I won't leave my big face on the screen. I'll move quickly to slides. Everybody loves slides. Let's see. So here's the deck, and hopefully this will be somewhat self-explanatory, but I'll talk about this. So I've been working for Tygraph for quite some time. This is the thing that I am most excited about at the moment in the problems that we're solving for people, and we're finding this is we're getting a lot of interest, which is good for us because I'm in sales and we want to sell things, but also hopefully this will be quite interesting to show just where the market is going as far as the whole idea of data-driven business is concerned. As you can see on the title here, it's all about solving big operational problems with very much an emphasis on the word operational. So this is kind of trying to take everything we've learned from the BI side of the world and the big data side of the world and start to see how we can apply those same skills and same technologies and techniques to the basic functions of a business, the operational aspects of the business. And that kind of adds a whole extra dimension of problems, a whole extra dimension of requirements that need to be covered. And I'm happy to say that TigerGraph, who I work for, we are very well positioned to actually address those. So in 2020, as it says on here, we did some work for JLR where we got their operational response time for when there was a specific problem with a supplier or with a part that was supplied. Normally to decide what they were going to do instead of that would take about 3 weeks. This is for car manufacturing, which is obviously very complex. We got that down to 45 minutes, and there are a number of talks and videos which are available on our website, which talk about exactly how we did that process. I'll cover them briefly on here, but just to give context for what we're trying to do now. Now this year, and this is where we get into the operational space, is this, we're really emphasizing trying to get it down from 45 minutes to real time. I'll talk about what that means, since it's a very highly abused term, real time. It'll be able to give you some idea of exactly how we're doing that and what we mean, what are you doing in real time versus what generally takes a lot longer. So, question, who am I? I've been building real-time applications for all sorts of data, big data and small. We used to call it fast data, is what I like to call it. Been doing it for a long, long time. Way back around about 1998, I built Morgan Markets for JP Morgan, or as it was then, JP Morgan Chase now, and that's still very successful for them. I was a lead enterprise architect for Toyota Motor Europe for many years, thus my abiding love for cars, and I bore everybody to tears by always using car analogies. Well, that's why, is because I spent so much time at Toyota. But particularly that gave me tremendous insight into what are the operational issues and just how complex and how costly it is to build a car. The car manufacturing industry is probably as complicated as any industry in this respect. So it represents some fairly unique challenges, which definitely transfer to other companies as well. But it's you want to know that you could scale to that if you wanted to. I was also chief architect for Zap, which nobody knows what Zap was anymore, I don't think. But if you do any real-time payments in the UK, particularly push payments, maybe you've got Ping It or Barclays or anything like that there, or Mobile Me, there's a number of different things, even on some websites, that goes over Zap. So it goes over that. It's actually the national push payment system for the UK. That was bought by MasterCard, Vocalink, and now it is all across the US. That is as real time as it gets and as important as it gets, because generally payments, you can't get payments wrong. So really that gave me a tremendous insight into just what it means to have to be reliable and secure, and just how quick something has to be. That has to work on every till, everywhere, all the time, with almost no delay whatsoever. So that's what I mean by real time, is not just sub-second, but millisecond response time is required. I then did environment operations for BP Trading, which gave me an abiding, I wouldn't say love, but the challenges of an operations manager. How do you operate things? If you are an operations manager, it's a uniquely stressful job, particularly in complex environments. Mainly because if you get anything wrong, then the business stops. And stopping businesses is rarely something that you want to be anywhere near, and particularly when everybody rings up the operations manager if anything goes wrong. So this solution that we're doing here is very much addressed at these people who have to deal with operations management. But this could be fraud, for example. So fraud detection is an operational function of any bank or payment operation, and getting that wrong is real money. In the anti-money laundering context, it has significant issues from a regulatory point of view, but also just from the general point of view of stopping people from stealing money. Operations is a really big deal, and it's also a place where there is significant pain in most of these companies. And the reason there's pain is because you have to have a human in the loop. This is something which is very difficult to automate. The problems are either very complicated, or so therefore not something that you can anticipate and therefore standardize and automate, or it's just so important that you absolutely have to have a person saying yes or no and doing it in an informed way. And the tooling that we'll be talking about here is very much focused on supporting those functions. And 5 years applying advanced NoSQL to big problems. Yeah, whatever, yada, yada. I imagine most of the people who've come to this conference have probably got that one, so it's no big deal. So the standard page we have for what does Tygraph do, or what is Tygraph. So this is almost the summary page. It's probably the most sales-oriented slide that we'll have today. It does advanced analytics and machine learning on connected data is the headline, but what is it? It's a distributed analytic graph database. It's distributed because we work transparently over a cluster. And nowadays we wrap that in cloud, which I'll talk about later. But the point is that it can be as big as you like. We've got 30 terabyte systems running. These are all in memory. These are all millisecond response time systems. Most of the biggest systems are actually the most difficult and the ones with the highest constraints in terms of response time and also consistency of response time. So you can't have delays. We also do advanced analytics. So the sort of advanced analytics we do are graph analytics. So graph analytics? A graph is really a series of data which is connected. I'll talk a little bit about the model and how that model works, but it's that idea that you connect all your data together and you can query all of that data very, very rapidly is kind of the heart of graph databases. And then when you have data that quickly, then there are certain functions and techniques that you can apply to it that actually improve the world. So they make fraud detection better. You get fewer false positives, you get fewer false negatives. So you're detecting more fraud, but you're doing it without increasing the noise at the same time, which is always a bit of a problem. The other thing is here is the in-database machine learning. So we can do, generally we support machine learning externally, which is the conventional way. And for that, it's really resting on the idea that we can provide a lot more data more quickly to the machine learning models in order to learn. But if you do that, then in order to run those models in the real context, in the real-time operations particularly, for example, then they still need the same data at the same speed. And so as a result, we act very well as a streaming platform underneath those models. And those models run separately. And for the very highest performance setups, there's one on the right here for China Mobile, which is doing fraud detection on phone calls, finding scam calls, doing 750 million calls a day, to give you an idea of the sort of scale. The response times for that, it was requested that they be between 20 and 10 milliseconds response time to actually run their model. So what we did was we actually built the model into the database, and TigerGraph allows you to do that kind of advanced thing. It's not something you do every day. You generally involve us to help you to get that sort of consistent response time. So it's definitely not something that we could say, oh yes, everybody can do this. But those facilities are absolutely available. China Mobile doesn't ring us every day to change their models and all the rest of it. We simply set up the structures and they ran with it. And so that kind of capability is definitely available. So that's the big picture stuff of what is TigerGraph. And these slides should be available afterwards. So all of the references on here you can look at. I'm not going to just read my slide. This is the way I kind of boil it down for the operational use cases, and really represents what I want from a product if I'm an operator and I want to buy it. So first of all, I want to be able to address my entire estate. And so therefore size is significant. In Jaguar Land Rover, for example, for 6 months of production of cars, for them, that represents around about potentially 4.5 billion parts involved to be able to build all of those cars. That's quite a lot of data. That is no problem at all for us. They run that on commodity machines in Google, GCP, and it runs very well. So size, you don't want any limitations. And so what I've talked about here is, when it says big, up to 30 terabytes, and we're hoping to go bigger this year. I think we've got a 100 terabyte possibility this year, which we're just testing at the moment. No partitions, so it's just one big database. You're not having to artificially segment the database in order to get performance. That performance is completely comes out of the box and is very consistent. And distributed, you run it on as many boxes as you like. Every box is exactly the same. So that means that, again, you get a very predictable way of spreading your data without having to worry about it too much. You basically just set the dial to the number of boxes you want for the amount of memory you want, and that's it, it works. The speed, I've talked about millisecond latency. It's not just about being able to get the data quickly, it's also you need to be able to get data in and out of the system very, very quickly. So we can do that. We consistently can get millisecond latency while inserting data at gigabytes per second is up there. That's not a insignificant system that does that, but there are no architectural challenges around that. It really is just a matter of scale. And the other is massively parallel processing. So we do everything with what we call thread per edge. What it means is that every operation, every tiny operation, almost the machine code of the database, if you like, occurs in parallel. So we get maximum parallelization. So we generally will maximize the usage of the hardware across all of the CPUs, across all of the machines. And indeed, we even have a mode where even individual transactions can be run across all the machines in order to get the maximum speed out of the cluster at any one time. And that's for any individual transaction, and it works automatically. When you write our code using our language, GSQL, which is soon going to be part of a standard over the next couple of years for graph languages, that happens automatically. You don't have to program towards that. You simply need to program in our language. You don't have to worry about messaging. You don't have to worry about parallel features. It just kind of works. So in that sense, it's a little bit like Hadoop in that Hadoop kind of dealt with the parallelization for you. We do the same thing, but in an interactive environment. I forgot to say also, we are an ACID transactional database as well. So you're not sacrificing any safety of your data in order to get this kind of capabilities. And finally, smart. We talked about smart before in the sense of being able to do artificial intelligence and machine learning. For me, the smartness is in the ability to use our product extremely quickly. So we've put a lot of time and effort into making the product as easy to use as possible, and we continue to do so. And every release, it gets better and better at this. So now we have scaled clusters which can be built completely on demand. You literally press a button on a console and it builds the cluster of any size you like at any time you like. We can do that via APIs, so that if you've got a DevOps system, if you've got CI/CD systems or any of that sort of environment where you want really to be able to script to create the machines that you want when you want them, we are now doing that for you. It builds it, the API returns, your cluster is up and running immediately. You can then use other APIs to then build your schema, to insert your data and so forth. The point is that we've kind of taken a lot of that integration complexity out as well. We've also added, and we add every single day, more and more connectors outward. So we've just added a Snowflake connector, for example, and that's quite useful if you want to enhance your existing data lakes, your existing batch data systems, which are brilliantly adapted to what they want. If you just want to enhance them with a bit of this graph goodness, then we try and make that as easy as possible so that it's not another technology churn problem. It's really just an incremental addition, and you can do it on the basis of value. So you do the bits you need when you need them, and that way you can always demonstrate ROI on all the technologies that you add, which is often used to be somewhat difficult. It always used to be a bit of a shot in the dark with new technologies. So scale cluster built on demand, billing via the cloud, which is important these days because you just want to send money to one place. You don't particularly want to be sending money to 15 different people. That's particularly in the cloud world. Again, you want your services to appear native and fully integrated with data ops pipelines. That's just the point, that these are very much cloud native capabilities. And so you should now, I believe it's not quite released, or it may actually be released today on Google Cloud, for example, but it's already on AWS and Azure. Effectively, you can specify TigerGraph in the same way that you would specify any of the cloud native solutions as well, which again, it goes back to this smart, making it easy to consume, making it so that it's not such a big risk, so that you can try stuff out. And when you see the value, you can go ahead with it, and you've really not lost anything except a little bit of time. And of course, you'll have learned a little bit more about the problem that you're trying to solve at the same time. Getting back to the operational problem statement. So the question is, and this is what operators have to think about all the time, or at any level, be it from COO downwards, when something goes wrong, what do you want to know? The first thing you actually want to know when something breaks, because there's always something broken, who's affected. So you want to be able to prioritize. In any complex system, we have customers with millions of moving parts, all of them important in some way to the way things are working, both in data as well as manufacturing operations. There is always probably about 100 things broken at any one time. So prioritization becomes important. And so the first thing generally you think of, although it might be slightly counterintuitive, is who is affected. So the idea is, if this breaks, who's going to be ringing my boss asking why I haven't been fired yet? Who is going to have a problem? Which of my customers, effectively, is now not able to do what they need to do at the time they need to do it? And different people will have different requirements. There's different criticalities. There's the number of people involved. So all of these things are why you generally ask first who is affected, in order to work out whether this is a big problem or not. Because if no one's affected, who cares? If an entire system can be down, but if nobody's affected, then you've got time to fix it. You don't have to worry about it so much. Even the tiniest thing, the tiniest problem, if it affects a lot of people, and often they're the worst ones, we always hear about them in the news. Oh, somebody made a small change somewhere and that broke the entire system. That's why who is affected is such an important metric. How big is the problem? This represents how many people are affected fundamentally. So how many of my customers are going to be affected? What is the scope of the problem, if you like? Only then do you really start thinking about, okay, something's broken. Usually on an operations screen, you know what's broken because you can see there's a big red flashing light somewhere. So now what you want to do is you need to know how to fix it. And to do that, you need to know the cause of the problem. And causes are very complex things, and often they are upstream. So for example, if the problem is that somebody has not received the data they expected, or they didn't receive the car they expected, or something broke when they tried to use it, when somebody bought any product, the cause of the problem is not the broken product. The cause has to be something that actually was further upstream, if you like, of where you actually found the problem to occur. And so what you need to be able to do is work your way upstream to find what of your many, many problems actually caused the problem there. And that is immediately actually something that's very difficult and starts to become a bit of a problem in conventional systems. And what I'll show in the demo, which I will show later, is that finding the cause of the problem when you're dealing with graph databases, when you model it in the way we're suggesting, actually becomes entirely trivial. Yet that, when things go wrong, is usually the major problem. So immediately we can start cutting down the issue around it. Who should I call? Okay, we found a problem. We know what's caused the problem. We're busy fixing it. But the next thing you want to know is, who should I call to say, look, something's broken, we're fixing it. And that's really important to get ahead of it. So now you're starting to actually talk to your customers. And they usually, you can avoid that call to your boss to asking what's gone wrong if you can proactively go out to them and say, look, we found a problem. We're dealing with it. We know where the problem lies. It'll take this amount of time to fix. Please do whatever you need to do to survive for the next half an hour to an hour while we try and get this fixed, for example. Then you have root cause. This is when you get into the strategic side. Root cause analysis, 5Y in manufacturing, is, again, something that takes a very, very long time. And generally, there are multiple root causes. I think a lot of the time, it's almost as if there's only a single cause for these events. It's not. Usually, there is multiple levels of factors. For example, in an overload situation, usually it's because you've got two things that have gone wrong. One is you couldn't handle the volume, and the second is you threw that volume at something. You put too much volume at something. So there's always two root causes there, either one of which, if you didn't have that happen, wouldn't have been an issue. So root cause of the problem is finding the root causes. You actually want to find all of the root causes, so everything upstream of what you've done. And then you need to work out which of the root causes you should spend the money on to fix. And really, that's a question of, first of all, how much should I invest to avoid this problem in the future? And around that, how much should I invest is, of course, are the limits of what's my budget here? And what am I allowed to spend here? How should I focus it? How widely should I be able to fix this problem? Because generally, if you have an infinite amount of money, you can make a system completely bulletproof. But nobody has an infinite amount of money. So really, this becomes really important from the strategic and the planning sense. Excuse me. Important factors, just to make the point of why this is a big deal. So this is, I kind of guessed when I first did this, and then I did some research to back it up. So I said originally, system downtime can be, over €1 million a day, which is about 700 euros a minute, which is a kind of a big number. But any large enterprise, actually, the chances are that that's not an unrepresentative figure. But then I actually looked at some research and found that these research company in manufacturing called Thomas actually went and asked loads of car manufacturers, how much does it cost? What does downtime actually cost you for a manufacturing line, a factory? And it turned out it was on average, so this is not the maximum, this is the average, was $22,000 a minute. So that's an extraordinary amount of money, but also what it represents is an opportunity. If our previous response time was 45 minutes, so for 45 minutes, people were kind of juggling to try and get things going before they knew what they needed to do next. 45 minutes, that at 22K a minute, in principle, that's an awful lot of money. It's like $900,000 in my bad maths. Time is money from second to second. So now this real time, this idea that a real time information system might be able to support an operator, it starts to look like is actually a decent value proposition. And that is key. Millions of process events a day operating on billions of parts. I talked already about how big this problem is. So it's not something, it's something that you can usually get away with legacy approaches, relational databases or whatever, anything that's not a graph. you can get away with it for small scale, but very, very rapidly you get to the point where it just doesn't work anymore. And so you start needing to look at a more efficient way of working. This isn't necessarily something that you can anticipate. So it's very difficult to be automatically efficient when you're doing these things. So you do need an intrinsically efficient way of doing it. And you also want something that doesn't architecturally limit you too much, so that you can only investigate in certain directions. So this is the point. When things go wrong, they're almost always not anticipated. And that's the point. And they're also rather complex. Internal issues cannot always be anticipated. So it's not just about when things go wrong outside, it can be anything on the inside. A wire could break. The classic cliche is that somebody unplugs your mainframe to plug in a vacuum cleaner. It's that kind of internal point where it's such a complex system that any small thing can actually have very wide scale unanticipated effects. So, and the model, if you want to make a model like a network model we talk about, since these are all interacting processes in a network, that model is very complex because it's big and there's lots of pieces and they're all talking to each other. It's interdependent, which means that there are a lot of links between things, and you can see where I'm going with this, why saying that graph is a good way of doing it. So there's lots of linkages between all of these elements, and it's dynamic. Things are changing all the time. We've got car manufacturing, delivery, operations, anything in the real world. Generally, you're fixing it and changing it all the time. Data operations in particular, you're changing your schema, you're changing your data, you're changing your reports every time there's something new comes along. And so it's extremely dynamic. So a very static model is not going to work for you. You need something that not only can deal with this network of activities, but also that you can change at will and still maintain the degree of control and benefit that you're looking for. And also response time, speed, all those good things, they need to be able to automatically handle the change as it comes along. So what do? We create a direct model of the network, which very approximately in manufacturing you talk about in terms as a digital twin. So what it is a bunch of things that talk to each other. That's really the basic model. And what does that look like? It looks like nodes, or vertices in a graph, which are the things, which are entities in a entity relationship model. And you have the ways they talk to each other, which are the relationships between those entities. A graph database fundamentally models exactly that. It models entities, just in the same way as you would in a normal database. It's a thing which has attributes. And relationships, which are the links between those things. Now, the relational model, when it's been implemented in a relational database, is not direct. Then at that point, they start talking about normalization. You'll find that the links are not expressed directly. It's really cut down because that made it work well for the technology of the time. What we have now is the capability to really go almost back to the future to take the original idea. If you're into database modeling, then there's a thing called a Chen model. And the Chen model looks at links and entities separately, and that's exactly what graph databases do. You have the entities, the things of data, which the individual items. These are in a manufacturing sense are often things in the real world. It's actually a part, it's actually a car, it's actually a machine. And the links between them, which of course is how things travel between those individual elements. And that's exactly what a graph database does. And because it does that so directly, that automatically gives us efficiency. And because we treat the edges and the entities separately, it also gives us this dynamic capability that we are looking for. So graph databases on their own, just the model itself gives us a huge number of advantages. What the different implementations do is different degrees to which they can handle the other elements of it, which is the scale, the speed, and the analytics over the top of it. So what's in that network, just to make the point about it being big, all the parts, all the success failure events. The whole system has to empower the humans in the loop, which comes back to my point that these are the human beings are at the moment kind of the weak link in an awful lot of these automated systems, but they're also the essential link. They have that basic characteristic that people are intelligent, people can take a problem which is very ill posed, where there's so many possibilities, and they can go out into the world and they can investigate. So really what we're trying to do is try and help those humans to be able to be as good as, if not better than, the machines, to get away from this problem where they are actually the weak link in the process and actually make them the strongest link in the process. They need to be comprehensive, complete, and accessible to the business. So when I say comprehensive, it's got to cover everything as far as possible that we care about. It's got to be complete, all the data, please, including history data for a lot of systems. And accessible, you want it so that the business people can actually do their job without requiring an army of technical assistance when they're trying to do it. We much rather if those capabilities were presented to them in ways that they can work directly, because if they can work directly, first of all, it's more efficient, but also it gives them a tremendous sense of agency and power, their ability to actually do the job. Network change events. We talked about dynamics. You have to be able to have network change events and score and prioritize failures as they happen. This is the idea that you shouldn't have to press a button. It should be automatically and continuously adjusting your views, be they dashboards or however you want to look at it, in a way that allows you to have this continuous, very real-time view of the world as it's happening outside it. So your digital twin, if you like, looks like what's in the world, no delay. And that's true not only for the general operational sense of things happening in the network and breaking, but also it needs to reflect very directly and in real time the change events. So when somebody changes your network and things like that. So, another point which actually is interesting. I'm not going to stress it too much, but once you have a digital twin model, pretty much everybody in the business should be able to understand it, because it's basically a high resolution picture of their business as it's happening. And so you can use exactly the same model for different things. It can be for root cause analysis, for risk analysis, for forecasting, for optimization. They're all going to work on the same model. Now, I'm not necessarily going to go into all those details, but that ability to always be talking about the same thing, no matter who's talking about them, that creates a very powerful feedback loop and really gets to the point where the idea of a data-driven business or a data-informed business becomes a reality, because now the data tools are directly serving the people who need that information. So I think it's a very powerful concept anyway. Right, what's next? Applicability. We talked about manufacturing. Don't worry, I'm not going to read all of this. You'll be able to see this afterwards. But also data operations, very important. So it's not unusual to have thousands, if not millions, of data of information transfer activities occurring inside an operation, and not just for reporting, but also for the basics of an operation. So a payment system is really just information moving around. In a retail system, they live and die by the information that they receive at the point where they receive it. So tills have to have the money in them. You need the pricing, you need your stock, you need your staff, you need all those resources. All of that utterly depends on your data operations. So it's quite important for your business that they work. And supply chain is the rather obvious one, the logistics, the tracking of stuff. Where is my stuff? Also, where has my stuff been? And material traceability we'll talk a little bit about, but that's become more and more important, where people really do want to know when they buy a product exactly what has gone into this product. And when I say exactly, they want to literally know who picked the beans that were then turned into this coffee or this chocolate bar. Here's my simplified entity model, just to give an idea. JLR did try to do it in BigQuery, the biggest BigQuery that you could possibly do for some of this stuff. It was anywhere between a 23 and 36 way join, which is obviously not only impossible to write, it's impossible to run. But this represents the end-to-end. So any complete or comprehensive system has to actually handle all this. But this immediately enforces a technical silo model for their data, unless they can link it all together, which is what we did for them. I think they did try. I think they had one query running for 2 weeks before they just shut it down. It just wasn't going to work for this. And actually, that was the point where they asked us to see if we could help. Demo, finally. Let me show you what this looks like. And this is a prototype that we're putting together at the moment, really to illustrate this capability. But these are real components that we are due to publish very, very shortly. And so the idea is that you'll be able to actually use these directly. And also what we want to do is build out this corpus of instructions so that for at least the simple use case, at least in principle, people should be able to do it on their own. It should be really easy. It's just a matter of mapping their data. We really want people to be able to try this out without feeling like they're having to invest a huge amount of time or make a huge commitment in this. So here's the real prototype application. This is a very small network, really, to illustrate what's going on. But nevertheless, it's still already got certain levels of complexity. You can see that from end to end, from the parent on the far left to the customers on the far right, there is anything 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different steps involved, all probably different systems. Some are delivery systems, some are processing systems. So it's starting to give a sense of the technology involved. And actually, the vast majority of database systems, even most graph databases, already have difficulty dealing with querying end to end on things like this. So what we want is to see whether we can satisfy those problems that we wanted. If you remember the operator, you wanted to know who he needed to call, how big was the problem, things like that. So this is tied up to a database so that you can see what it's done. I want to make the point, this is very much real time. Yeah, this is very much a real time system. And there we go. If I actually put the thing in the right place, you can get an idea of just how quickly it can get information out of the database. So what we can see is there is a problem on the right-hand side here. Let me zoom in. So imagine this is a car that was bought by a customer, very modern mobile, I think you'll agree. And the first thing they're going to want to do is, okay, so there's a problem with my car. Who is this affecting? So first of all, we need to find the problem. So we can do that straight away. There you go. Instantly, problems up here. Who is this affecting? I click on this. I press downstream. There we go. So now we can see that this problem affects these 3 people. I've basically answered my first 3 questions immediately, like instantly. There is no delay at all. I generally talk quickly. I cannot talk quickly enough to really give an indication, which is why we did this demo, to make the point of just how fast this is. So that's already put us in a very good position. We know what we need to fix and where we need to fix it. We know who we need to call, and also we'll have the customer information associated with this so that we can actually work out how important those people are, whether this person's requirements is actually where it's immediate, in other words, or whether actually it's going to be a day or 2 before they actually need this information. So actually, we've probably got time to fix it. We don't need to ring them up and bother them at all. That's great. So now we get to the strategic point. And just to the point, this is done across the entire network. There is, we can do this from anywhere. You know, if I want to do it for this one, upstream. Okay, there's a problem here. Let's have a look upstream. Oh, here we are. We found a problem here. Who does it affect? Downstream. This is all the systems that are affected. It's very quick, very easy. Coming back to our original, we had our problem with our framework has clearly caused a problem for us. And so now what we want to do is look for root cause. So we use exactly the same process. I've got buttons on the top right as well as on the screen. I can do this. So now we're seeing the entire chain of events to which are associated with this. And so the next question is, how much money should I invest in this and fixing this? If this is the root cause, and there's actually a bunch of things up here, if that TigerGraph node here is actually the root cause, how much money is it worth spending to actually fix this? And so the question you have is, if I had a bigger failure here, just how badly would it affect me? And actually what we see is that actually it's got a fairly significant effect over the estate. So now what you've got is a risk-adjusted approach to investment in terms of fixing root causes. And that is exactly the information you generally need as a portfolio manager to be able to look at this and go, okay, actually that's quite important. I think I will fix that. Whereas if the root cause didn't have effect on anything beyond just my view. Maybe I just want to fix view so that it's more permissive, that it can handle the change events upstream so that it's less of a problem. So it allows you to basically go into that strategic mode for root cause analysis and also investment to work out whether it's worth doing something. And that sequence, as you can see, I've pretty much done the same thing every time. I've looked at the thing that had the problem. I've looked upstream to find out what I need to do about what potentially is involved. I've traced that down to find the problem. Then I've looked at everything that depends on it. I've looked at to work out what it's worth doing. So that's almost the same process over and over again. And because it's very standardized and simple, it means that it's very easy to implement this across pretty much any setup. One thing we can also talk about is for change management. If you're doing change management, you'd say, well, I'm going to do a change here. Say I was going to make the change to Tygraph, then you do the same thing. What depends on this? So do I need to spend an awful lot of time creating a duplicate system and all the rest of it? Or is it okay if I turn it off and just make the change anyway? Being able to see what depends on a particular element means that you can take a risk-adjusted approach to how you actually approach that. And again, from a planning point of view, that's exactly the information you generally need in order to plan, and it allows you to spend the appropriate amount of money rather than always do the belt and braces approach, which is going to be expensive, or equally compromising where maybe you shouldn't compromise. And so you might need a more robust approach when you come down to it. And that is the demo. I hope you liked it. I can see some questions. I'm going to jump to them in a second. I just want to make sure that, oh yeah, okay, it's just architecture at this point. So that's kind of the tech. Let me look at some questions. Wonderful questions. Is this tech useful in IT network monitoring applications like observability and cybersecurity? Yes, it is. The key is, if anywhere you've got this network of interacting entities, anywhere where you have signals, so events that actually represent something that you care about, then usually you want to be able to get a sense of it's generally known as the blast radius problem, is how big a problem have I got right now? Is this small problem that I'm seeing actually indicative of something that could be a much, much bigger problem? Then exactly what you're talking about there, observability, cybersecurity, yes, it gives the sort of information you need so that an investigator can look. The example we have for cybersecurity was that if a printer starts sending emails, generally that means that something's a bit strange. Either your printer isn't a printer, or somebody's hacked your printer, or something has gone wrong. Equally, if somebody accesses an API, but you'd have no record of them accessing the system internally or through a firewall, then the question is, how did that actually occur? So this idea of being able to look for correlations or look for things that maybe are a little bit unexpected, and then to really search through the system to work out the context of what you are seeing, it's that context that informs you as to whether it's a big problem or not. Hopefully that answers the question. For object, product, people, physical infrastructure tracking, how do you coordinate between IoT, RFID, and picture recognition devices to set most accurate information? Okay. And I'm going to give what may be a bad answer, but it's actually the right answer, is we don't. We are the center point. So the information comes to us, but there are, particularly for IoT, RFID, picture recognition devices and things like that, there are extremely good devoted technologies that do that. And we're not going to try and do everything for everybody. What we do is we provide this contextual linkage, and we rely on other services to effectively translate the signals from the real world into something that's meaningful for us. This is true for natural language processing, for, as you say, for picture recognition, and exactly the kinds of things where you really want something that's a bit more specialized in order for it to be efficient. And often people have them in place anyway. So that's generally how we deal with it. In terms of coordination, how do they talk to us? We have standard interfaces to standard message buses. So whether it's the message interfaces on the cloud, or Kafka is very common, or we expose REST APIs for everything. So if you've got a service that can just do a web call to our database or to a proxy in front of the database usually, but then that will just work. So we really do try and make it as easy as possible for the information to come into our system. So any other questions while we're there?
I've got one here, if you like, Richard.
Sure.
It's do you store all the information on the graph?
Actually, good question. We don't usually. Now sometimes we can, but if you remember, it's a memory-based database, and memory is not a cheap commodity. So usually what happens is the data comes in, and particularly raw data. I mean, somebody talked about pictures. You want to put them in a raw data store. Unstructured information, documents, scans, all that kind of information, that usually lives in data lakes, and that's absolutely the right place for them. We don't try and replace the functionality of the data lakes or the Hadoop or all of those systems that are in place. What we need is the information that's required to serve the particular function here, which is this operations function. Now, the applications you saw, I mean, I showed that application with the car. You'll notice that pictures appeared on the top right. Those pictures actually, that application sits across a number of microservices. One of those microservices is the graph, and the other microservice is the picture server, and another microservice is the detailed information server. And so that way, as far as the application is concerned, it's all beautifully coordinated. But in our database, they're just hyperlinks, unless it's information we need to do our analytics scoring on, then of course we bring it in.
Perfect. And the TigerGraph language you mentioned, what's the best way to get started with that? Just get a free trial, try it for yourself, or communities or meetups, or I don't know, it'd be virtual at the moment, but is there some ways to get people involved in the first instance?
Absolutely. We have a really tremendous community, developer relations team. If you go to TigerGraph.com, then you can go via the developer links. So you can get past all the sales stuff and go straight to the developer and community stuff. And there's lots of resources there. In fact, I mean, I've got at the end of this deck that I showed you, I didn't put it up on the screen, but hopefully it'll be available for people. Then there are various links to, there's Twitch. We're even on Twitch. We're that fashionable these days now. Or maybe Twitch is old now. Maybe we should be on TikTok or something. I don't know. Anyway, the point is that we have a tremendous developer community. They're incredibly positive. I hang out there as well, so you'll probably see me trying to answer people's questions. Engineers answers questions. The entire company is very much orientated towards, I don't know, trying to get into people to understand just why we're excited about it. It's not just because we're paid to be excited about it. We really do like this stuff, and because you really can solve amazing problems. But obviously, we'd rather people were solving their problems and then telling us about it, rather than us pretending we know what their business is. So educating them is important. There's loads of resources on there. There's training videos, even on YouTube, Graph Gurus. I could give this laundry list. The point is, we absolutely help as much as we possibly can. And because we understand this is new, a bit weird, and it's not entirely obvious how to solve problems with it. It sounds great, but how is this good for me? Then you can go to that. Once you do want to get into that, then tgcloud.io is available, and that has free tier, so that you can actually run instantly, just like we do. This is the same system we use for production cloud. So you can run a real Tygraph with all the features intact, and you can really try it. And there's toolkits on there as well you can try. So if you've got a specific area you're interested in, then fire up one of the toolkits, and that gives you a starting point, if you like, of going, all right, I see. So here's a supply chain toolkit, or here's a fraud toolkit. There's loads of them. And that really helps if you want to go direct to the examples, if you like, rather than go through the sort of academic element.
Perfect. Last question then for you. Obviously, lots and lots of different applications for this kind of technology, and you mentioned a few. Is there anything coming up, or anything you can see in the future that you're excited about? So I know you're not just dealing with everything that's happening now with one eye on the future. Is there anything that's looks particularly exciting?
Yeah. So the example I gave, first of all, the operations thing is quite new. I'm pushing it really hard because I care about it because of my history. Because I've had those phone calls in the middle of the night. I've had the buzzers go off, and it's like, oh no, system down. It's like, okay, no more information than that. System down at 3 o'clock in the morning. You don't want that. So the operations thing is really important. But what we want to do is, we've talked about the initial part of that, which is just show me what's broken, show me why it broke, show me who I need to ring. So that initial stuff, and a little bit of the forecasting and planning stuff. But graph analytics are extremely good, can take you a lot further than that. The next step we're doing is, in forecasting and planning, is to say, where could my system break? Show me how fragile, where are the fragile bits of this giant system? Where are my single points of failure? Where is it likely for something to break? And that starts to give you that ability to maybe get ahead and say, so that wire was unplugged the other day, but what we didn't realize was that meant that this system over here has become fragile and has become a single point of failure. And that's extremely likely in a very dynamic network that this will change all the time. So being able to have like a heat map of that is really important, so that people can maintain their assurance of reliability, speed, or indeed security, to make sure that their security systems aren't leaking, that they're all still within the correct setup. So that's the second part. And the final part is, we want, and this is something we can absolutely do because we already have the algorithms for it. I just want to build it in so that people can see and make it easy to use, which is we want people to look at their network and be able to establish a goal for the network to say, I want to guarantee that something like this will only, I have 5 nines reliability across the entire network. And what it will do is it will actually adjust everything in the network till you achieve that goal, but within all the constraints. So that might be within cost constraints, it might be within a certain amount of change constraints. So this idea of being goal directed towards a particular end, and have the system effectively calculate that for itself. So it gives you what is effectively a prioritized list of targets for investment and work. Then you're getting into a very sexy area of operations where you're able to, with great confidence, say, my system is now compliant, or my system is now reliable, or my system is, these are the weak spots which we need to address. And that's when you're starting to really optimize your system automatically. And I think that's something that is almost impossible to do on a large scale network without these kinds of analytics. So that's kind of a new capability in the market I want to bring to, using exactly the same model, just getting different levels of sophistication.
Perfect. Well, thank you. Thank you for that. And thank you for a great presentation. Interesting stuff today. It's great to have you back, obviously. In terms of anyone watching who might have missed a little bit or want to go over a little bit, perhaps the demo, this is available on demand almost instantly after we finish, and you can go on it and rewind and pause and all that good stuff. You'll be able to go back to that resources piece that Richard mentioned when he was talking earlier as well. But I think with that, we're going to bid you farewell. Thanks very much again, Richard. We'll see you soon, surely, and goodbye to everybody at home. Thanks very much.
That's great. Thank you, and thanks for listening. Bye-bye.